So in this video, I'm going to run through how to write balanced redox equations, and we're going to do it in two ways. One, we are going to use half equations, and in the other way, we're going to use oxidation numbers. And what we're going to see is that the half equation method is probably easier, but a little bit longer, and the oxidation number method is then quicker, but you are more likely to make mistakes if it's a tricky reaction. So I'll start off, I'm just going to briefly remind you how to write half equations under acidic, and I'm also going to do alkaline conditions. So if it's under acidic conditions, the first thing I need to do is balance the atoms that are not hydrogen or oxygen. So I've got 2 sulfurs on the left, but I've got 4 on the right, so I'm going to need to put a big 2 here. And then if I look at my oxygens, I've got 6 oxygens on the left and 6 oxygens on the right, so they are balanced too. All I need to do then is balance my charges. So you can see here I've got 2 times minus 2, so I've got a charge of minus 4 on the left hand side, and I've got a charge of minus 2 on the right hand side. So to get this side to minus 4 as well, I'm going to add 2 electrons. The only thing I can add to balance charges is electrons. If I look at another example, I'm also going to balance this under acidic conditions. So again, I start by balancing the atoms that aren't hydrogen or oxygen, 2 chlorines on the right. To get 2 chlorines on the left, I need a big 2 there. And this gives me 6 oxygens. Now, I don't have any oxygens on the right. And when I'm balancing under acidic conditions and I want to add oxygen, I do that in the form of water. So to give myself 6 oxygens, I'm going to add 6 moles of water. But in doing so, I've now also introduced hydrogen to the right-hand side, 6 hydrogens in total, and I've got no hydrogens on the left. To balance those hydrogens under acidic conditions, I'm going to be adding H+, and in this case, I'm going to need 12 H+ in order to balance them. Now all that's left is to balance my charges. So I can see here I've got 2 of these. So I've got 2 negative charges and I've got 12 positive charges. So overall, I have 10 plus on the left-hand side. The right-hand side is totally neutral. To balance charges, the only thing you can use is electrons. If I've got 10 positives and I need it to be neutral, I'm going to be adding 10 electrons here on the left-hand side. So that's writing half equations under acidic conditions. We can also do this under alkaline conditions. So if I've got alkaline conditions, this is similar to what I had above. I'm going to follow exactly the same process, but I'm going to have to add a few extra steps at the end. So I start off by balancing the atoms that aren't hydrogen or oxygen. Again, this is chlorine, 2 chlorines on the left. I want 2 chlorines on the right. I now have 2 oxygens on the right. To get oxygens on the left, I'm going to be adding 2 moles of water, so plus 2 H2O. But in doing so, I've now introduced hydrogen. 2 times 2 is 4. I'm going to add 4 hydrogens to the right. Now, as this is under alkaline conditions, you might be thinking, well, why is she adding H+ ions? That's acidic conditions. But what you'll see in a moment is the extra steps that I'm going to add on at the end is going to get rid of those H+ ions. Before I do that, I'm just going to balance my charges. So I have got 2 times minus 1, so I've got minus 2 and plus 4, giving me a total charge of plus 2 electrons on the right hand side. Again, I need to have a balanced charges, and in order to balance those charges, I'm going to need 2 electrons. Now I've got 2 negatives and 2 negatives there, so 4 negatives and 4 positives, and overall it is balanced. Now at this point, as I said, because it's under alkaline conditions, what I need to do is, because I added 4 H+ ions, I need to add 4 OH- ions, and I'm going to do that on both sides of the equation. So 4 OH- to the right, but also 4 OH- ions to the left. So your rule is, wherever you add H+, you have to match that on both sides with OH-. Now when I do this, what's going to happen on the right hand side is the H+ and the OH- are going to combine, and they are going to form 4 moles of water. So I'm going to cross out the 4H+, cross out the 4H-, and instead I'm going to write that I've got 4 moles of water on the right hand side. To finish this off, I need to make sure I cancel what is the same on both sides. I've got 2 moles of water on the left, 4 moles on the right. I can now cancel those 2 moles of water out to be left with 2 moles of water on the right. And this is now my balanced half equation under alkaline conditions. I'll do another one under alkaline conditions. All right, so this is lead. Again, same first step as always, balance the atoms that are not hydrogen or oxygen. So I've got one lead on each side, that's fine. I've got two oxygens on the left, I've only got one on the right. Now your temptation here might be to just put a 2 in front, but in doing so, I won't have my leads balanced. So if I want to add more oxygen, I'm going to do so in the form of water. So I need to add another. If I add one molecule of water, then I've got two oxygens on each side. In doing so, I've added hydrogen. To add hydrogen to the left, I'm going to add 2H+. I'm then going to balance my charges. I've got 2H+, so two positives on the left, no charge on the right. So I add two negative electrons. Charges here now cancel out to give me neutral on both sides. Because this is under alkaline conditions, everywhere I add H+, I also need to add OH-. So I'm going to have two OH- ions on the left-hand side, and that means I also need to add two OH- ions on the right-hand side. Again, the two OH- and the two H+, they're going to combine together to give me 2 moles of H2O. And you can see I've got 1 mole of H2O on the right hand side. That will then cancel with that mole of H2O to give me 1 mole of H2O on the left, my 2 electrons, my PbO2, and then my PbO and 2 OH- on the right. Okay, so that's writing half equations under acidic and alkaline conditions. Same process for both, but with alkaline you have to add OH- on both sides to counteract the H+. Once you've written your half equations, you can then go on to write full equations. So what I've got here is I'm being told that S2O3 2- ends up forming S4O6 2-, just like we did at the start. And I've also got I2 forming I-. So I'm going to do this under acidic conditions. And what I need to do is write down two half equations. So the first one was S2O3 2-. That's going to become S4O6 2-. And I know that these two pair up just because they've got the same atoms. So when I wrote this half equation above, we saw that I needed a 2 here, and then I just needed 2 electrons to balance the charges. So that's my half equation for the first reaction. For the second reaction, I've got I2 becoming I-. Again, I need to balance my atoms, so I'm going to need to put a 2 there. And then in order to balance my charges, 2 negative charges here means I need 2 negative charges here. In order to write these half equations as full equations, your electrons need to cancel. I've got 2 electrons on the right hand side and I've got 2 electrons on the left, so they do cancel. And now all I need to do is write these two half equations as one whole equation. So everything on the left is going to stay on the left. So I'm going to have 2S2O3 2-. That's all that's on the left of the first equation, with the I2 from the left of the second equation. Because I know my electrons are going to cancel, I don't need to write them in. On the product side of the first equation, I've got S4O6 2-. And on the product side of the second equation, I've got 2I-. So I combine those two together, and that's my full equation. On this side, I've got a slightly different one. This would be an example of disproportionation, because I have got the same element is going to be oxidized and reduced. And I'm going to do this one under acidic, and I'll do it under alkaline conditions as well, just so we can see the difference, all right? So I take my IO-, and it turns into I-, and then I can also take my IO- and turn it into IO3-. So the same reactant in both in this case, but I'm turning them into two different products. So again, same approach. My iodine's already balanced. To add an oxygen, I'm going to add H2O. That gives me 2 hydrogens on the right. To get 2 hydrogens on the left, I'm going to need to add 2H+. I then need to balance this equation. So I've got 2 positives and 1 negative, giving me a total charge of +1. And over here, I've got -1. That means I'm going to need to add 2 electrons here at the top. So now I've got 3 negatives and 2 positives, so a -1 charge overall and a -1 charge overall here. So that's the half equation under acidic conditions. The one below, my iodines balance, my oxygens don't. Again, if you were to put 3 here, you would change your iodines and they would no longer balance. So to get an extra 2 oxygens, I'm going to have to add 2 H2O. Now I have got 3 oxygens on each side. In doing so, I'm after adding 4 hydrogens here, so I'm going to need to put 4 hydrogens over here, and then I need to just balance my charges. So in order to balance out my charges, I'm going to need 4 electrons here. These will then cancel out, leaving me with 1 negative charge and 1 negative charge. So they are my 2 equations. This time, when I'm putting these together, I'll see my electrons are not cancelling out. I've got 2 on the top and I've got 4 at the bottom. So what I'll need to do is this top equation will need to be multiplied by 2. And then what I'm going to do is I'm just going to combine these equations like I did before. So I'm not going to bother with the electrons, because when I do multiply by 2, I'll have 4 electrons on the left. They're going to cancel the 4 electrons that I've got on the right down here. But I am going to write this in, and I'm multiplying it by 2. So I've got 2IO minus. I'm going to have 4H plus. The bottom equation, the reactants, I'm not multiplying these by anything, so they just stay as is. Then I'm back to my product side. I've got 2I minus, I've got 2H2O, and then on the bottom here, I've got IO3 minus, and I've got 4H plus. At this point, you have to cancel out anything that is going to be the same. So my H pluses are going to cancel, 4 on each side. I've got 2H2O here, I've got 2H2O there, so they will also cancel. And then again, if I look here, I've got 2IO minus and then another IO minus. So in total, I've got 3IO minus. And if you don't simplify that, you're not going to get all your marks. So I've got 3IO minus going to 2I minus and IO3 minus, and that is it written under acidic conditions. I can do the same thing for alkaline conditions, all right? So I'm going to do the same equation again. I'm going to just write out what I had before. So this was my first half equation when I was doing it under acidic conditions. And then this was my second half equation when I did it under acidic conditions. And then all I need to do to make this under alkaline conditions is I just need to add in my extra step. So everywhere I have H plus, I have 2H plus on the left. I need to add 2OH minus on the left. I also need to add 2OH minus on the right. And then down the bottom, I had 4H plus on the right. So I'm going to need to add 4OH minus on the right, and then also 4OH minus on the left. So once you've added your OH minuses, you need to combine to form water. So on the left hand side, I'm going to have 2H2O there. And once I've done that, I can then cancel my water. So the water I have on the right is going to cancel into the water I have on the left. So now I've got 2 electrons, IO minus, H2O going to I minus and 2OH minus. So that's my half equation under alkaline conditions. Down at the bottom, I have 4H plus and 4OH minus. So they cancel out to give me 4 molecules of water. Here, these 2 molecules of water then will cancel. I no longer have 4, I've only got 2. And that is everything all cancelled out. So these are my 2 equations under alkaline conditions. Again, I've still got 2 electrons on the left and 4 electrons on the right. So I'll still have to multiply my top equation by 2. And when I do that, I get 2IO minus, I get 2H2O. I only had 1 H2O there, now I've got 2. Also, I've got 4OH minus here, and I've got an IO minus. They're my reactants. On the product side, I've got 2 times I, so 2I minus. I've got 4OH minus. And then down here, I have got IO3 minus. I'm not going to write in my electrons, and I've got 2H2O. So that will be my full equation. I need to cancel anything that's the same. So my 4OH minuses, they're going to go. My 2H2Os, they're going to go. I'll add these back up together to get 3IO minus, and here I've got 2I minus and IO3 minus. So again, we get to exactly the same full equation. All right, so that is how you would write these full balanced redox reactions using half equations. As I said, you can do so under alkaline or under acidic conditions. You can also balance equations using oxidation numbers. So what I've got here, just look at the first equation first. I've written out an equation. It's for an oxidation reaction, and I'm being asked to balance it. Now, if you try to do this normally, even if you were able to balance the atoms, you wouldn't necessarily have balanced the electrons, and you would still get it wrong. So what you can do, and what I'll do later, is you could take this equation and you could balance it using half equations. Now, to do that, I'd write a half equation with sulfur turning into H2SO4. And then I'd write another half equation using nitric acid, turning it into NO2. And I'd write those half equations, then combine it to form a full equation, and I'd end up with the same equation that I had here, but it would be fully balanced. Now that's obviously a bit of a long-winded way when they've already given you the equation and all they're asking you to do is balance. But if I take that approach, I know that my electrons are definitely balanced. Without taking that approach, you're going to have to use oxidation numbers, which is a bit quicker. So when I'm using oxidation numbers, all I'm going to do is assign oxidation numbers to the elements where the oxidation number changes. So sulfur here on the left is an element, so it has an oxidation number of 0. But if I get over here to the right, I've got 4 oxygens. All right, so I'm getting a -8 from the oxygen, and the 2 hydrogens are giving me +1, and that must mean that sulfur is +6. So I'm going from 0 to +6, so I'm getting a change of +6. All right, then if I have a look here at nitrogen, I can see in this case I've got -2 times 3, I've got -6, that's +1. Nitrogen is starting off there at +5, and over on the other side I've got +4. So it's going from +5 to +4, so my change there is -1. Now my electrons need to be able to balance. So you can see sulfur, we're getting this increase in oxidation number, so it's being oxidized and 6 electrons are being lost. But if we look at what's being reduced, which is the nitrogen, only 1 electron is being gained. So at the moment my electrons are not balancing. In order to do this, I need my change to balance. So I've got a +6 change, I need a -6 change. So I'm going to multiply this by 6. And what that tells me is that I need to put a 6 under the thing here that is being reduced, which is the nitrogen. So I'm going to put a big 6 there in front of the HNO3. Now that's all the information it's giving me, but once I know that I have a big 6 there, everything else becomes easier to balance. So because I've got 6 nitrogens on the left, I know I need 6 nitrogens on the right. Okay, so I never would have started with 6 if I hadn't been using this method. I've got 6 nitrogens on the left, and I've got 6 now on the right. My sulfurs are already balanced, 1 on each side. If I try and balance my oxygens next, I've got 6 threes. I've got 18 oxygens on the left hand side. I've got 4 and 6 twos are 12, and 12 and 4 is 16, so I need another 2 oxygens there, so I'm going to put a 2 in front of the H2O, and then that leaves me with 4 hydrogens and 2 of 6, and then 6 hydrogens there. So now not only are my elements balanced, but my electrons are balanced as well. I'll just do one more example of this. So again, you could take this equation apart and write 2 half equations. So the MnO4- would go to the Mn2+. You'd write 1 half equation there. Your other half equation would be H2S becoming sulfur. You'd write your 2 half equations, put them together, you'd get back to this full equation, but when doing so, you would end up with it balanced. So that is one way that you can do it, but again, it's probably a bit quicker to just use oxidation numbers. So here, if I look at the manganese here, I've got -2 times 4, so I've got -8. This means this must be +7 to give me a -1 charge overall. Over here, I've got a +2. So I can see here, I've got a change from +7 to +2. So I've got a -5 change. The other thing that changes from left to right is sulfur. So I've got +1 and +1. Sulfur is -2. And then over here, it is 0. So I'm getting a change in +2. Now, you could have to go through more elements to find out what's changing. I can just look at this quite quickly though and see that oxygen is in a compound in both cases, so it's going to stay as -2, and the hydrogen again is going to be +1 in every instance. So I know that's not changing. So it's the manganese and the sulfur that I go straight for, but you might have to use a bit more trial and error. Here again, I can see that these changes aren't lining up. So I've got this decrease in oxidation number here. So the reduction, so 5 electrons are being gained, but only 2 electrons are being lost. So in order to make these match up, I'm going to have to multiply this by 2, multiply this by 5, and then my changes align. That 2 there tells me that what's changing, the +7 down to the +2, I need to put a big 2 in front of it, so I'm going to put a big 2 here on the left hand side, and then my change here, the fact that I've multiplied by 5 means I'm multiplying this by 5. Again, that's all those oxidation numbers are telling you. After that, you need to balance like you normally would. So I know I've got 2 manganese there, no, what's called manganese, 2 manganese there. To have 2 manganese on this side, I need a big 2. If I've got 5 sulfurs, then I'm going to need a 5 there, and then I balance everything else as normal. So 2 times 4, I've got 8 oxygens. To get 8 oxygens over here, I'm going to need an 8 in front of the H2O, and then if I balance my hydrogens, I have got 8 2s are 16 hydrogens. I've got 10 there, so I'm going to need 6 there. So not only have I balanced my atoms, I have also balanced my electrons. I'm just going to look at what this looks like in the context of the exam. So in that revision booklet A, if we look at the exam questions, the first set, question 5 is testing you on this. So you've got 2 different ways that you can construct the overall equation. I think the easiest way is through half equations. So they tell me I'm starting with this dichromate ion and I'm turning it into Cr3+. I'm also starting with vanadium 3+, and I'm turning that into VO2+. Again, I'm just pairing them up based on the elements that they have in common. So those 2 match because they both have chromium, and those match because they both have vanadium. Once I've done this, I'm just going to use my balancing balance it under acidified conditions. So 2 chromiums, I balance my non-oxygens and hydrogens first, so I need to put 2 chromiums there. 7 oxygens means I need to add 7 molecules of water, and then I'm going to need to have 14 hydrogens to balance things out. Then I just need to balance my charges. So I've got 14 minus 2, I've got a 12 plus charge overall, and then here I have got 6 pluses. So to get these to balance, I'm going to need to add 6 electrons, then they'll both have a charge of 6 plus. Down the bottom, my vanadium's balanced. To get 2 oxygens on the left, I'm going to need to add 2 H2O. I'm then going to need 4 H plus. That gives me 5 positives on the right. I've got 3 positives on the left. So if I add 2 electrons, they cancel out. My electrons at the moment aren't cancelling. I've got 6 here and I've got 2 here. If I multiply the bottom by 3, I'll have 6 electrons in both. So when I put these together, I've got my Cr2O72 minus, I've got my 14H plus. I'm multiplying by 3, so I've got 3V3 plus, and I've got 6H2O. On the product side, 2Cr3 plus, I've got 7H2O, multiplying by 3, I've got 3VO2 plus, and 3 4s, I've got 12H plus. At this point, you have to go back and cancel or you're not going to get all of your marks, all right? So you can see here I've got 12H pluses on this side, so I'm going to get rid of these 12H pluses because I've got 14 over here, and then that is just going to become a 2, so I've got 2 H pluses there. Other thing I've got in common is I've got 6 H2Os here and I've got 7 there. Again, I'm going to get rid of these 6 H2Os. They will cancel in there, leaving me with just 1 H2O on the right. And that is my full equation. You can also do this using oxidation numbers, but in this particular case, it is awkward. So what you can do is it says, this ion reacts with this ion, so I'd start by constructing that equation. I'd write Cr2 reacts with vanadium 3 plus. To form a solution containing Cr3 plus and VO2. It does also tell you it's acidified, so you can assume you've got H plus ions there. And then I can try to just start balancing this. Now before I do, acidified solution construct the overall equation for this. So the first thing I'm going to do is I'm just going to start making sure, I need to make sure that I've got all of my the elements the same on both sides. So I've got my chromiums, I've got oxygens, I've got vanadium. Because it's acidified, I've got hydrogen there that I don't have on the right hand side. So in order to even that out, if I've got hydrogen on the left, to introduce hydrogen on the right, I'm going to be adding H2O. So now I've got a full equation. I'm going to use oxidation numbers in order to balance it. And the thing that's changing oxidation numbers is chromium. So I've got 2 chromiums there, and each chromium, so I've got minus 14, so I must have plus 12. So each chromium is plus 6, and it's going to plus 3 over here. And then the other thing I've got that's changing is I've got vanadium, which is going from plus 3. And I've got minus 2 times 2 is minus 4. And this must be, that's minus 4, this must be plus 5. 5 minus 4 is, yeah, plus 1. So my change here is minus 3, and my change here is plus 2. Now at this point, what you would likely do if we were doing this the same way as before is you would do this multiplied by 2 and this multiplied by 3, and then go back in and add those big numbers. But there's something to note here, all right? You're starting off with 2 chromiums on the left-hand side, and you're getting this decrease in oxidation number, so it's being reduced. But you've got 2 chromiums, so instead of just gaining 3 electrons, you actually need to gain 6 electrons because there are 2 chromiums. So if I need to gain 6 electrons, then how many vanadiums am I going to need? Well, each vanadium are giving you 2 electrons, but you need 6 in total. So you're going to need to have 3 vanadiums so that they can each provide 2 electrons, and you get the 6 electrons that you need in order to reduce those chromiums. So using my change in oxidation number, I'm going to be putting a 3 there in front of vanadium. And then again, that's the clue that my oxidation number is giving me, and then from then I can just do it as normal. So I've got 2 chromiums on the left, I'm going to want 2 chromiums on the right. And then the next thing I can balance will be my, I've got 3. Oh yeah, then I need to balance my vanadium. So I've got a 3 there. I'm going to need a 3 there. And then when I go back and balance my oxygens, I'll see I've got 7 there. And I've got 3 2s are 6 and 1 is 7 there. So they're already balanced. 2 hydrogens there. It means I need 2 hydrogens there. So it's probably a little bit quicker, but I think you're more likely to make mistakes if you didn't spot what was going on with the chromium and the number of electrons actually being gained. Then you may have made a mistake using oxidation numbers. There's another one down here. Oh, boom. Where you can use this again. You're asked to write an equation. It gives you the information at the top, and you can do it in one of 2 ways. You can do it using oxidation numbers, you can do it using half equations. I would again do it using half equation. So the student bubbles hydrogen gas through an acidified solution containing manganate ions. It forms aqueous manganese 2, a yellow precipitate, and 1 other product, all right? So if I start with my H2S, what's crucial here is that you understand this clue. A yellow precipitate means you are forming sulfur. So my H2S must be becoming sulfur. Your other half equation, you have got MnO4, and it tells you straight up that you're forming Mn2 plus ions. So there are your 2 half equations. You'll then write both of them under acidic conditions. You'll put them together and you'll have a full balanced equation. Your other option is to just use the use the instructions to write the equation straight off the bat. So you'll say that you have got H2S. It says it's acidified, so you've got H plus, and you're reacting that with MnO4 minus. You're turning that into manganese 2, Mn2 plus, a yellow precipitate is S, and 1 other product. You can see here you've got oxygens on the left, you don't have oxygens on the right. In order to introduce oxygens in redox, it's going to be H2O. So that's your equation. You'll have to balance it using oxidation numbers. You can see here that sulfur has got a minus 2 oxidation number, and then over here it is 0, so I've got an increase in plus 2. The other thing changing, manganese here is plus 7, and then here it is +2, so I'm getting a decrease in -5. At this point here, I'm timesing that by 5, I'm timesing that by 2, and I'm balancing. There's kind of no hidden tricks in this particular one. There's just one other one that I thought was a bit awkward to balance if you don't use a method. This one you have to balance using oxidation numbers. So it says iodide reacted. So this one, because you've got OH minus ions here, what you could do in order to balance the electrons is you could take this equation apart, write two half equations under alkaline conditions, put it back together again, and it will be balanced, and then you can just see how it's supposed to be balanced. But because it's OH minus, you need to take care that you're writing your half equations under alkaline conditions. So one half equation would just be I minus going to the IO minus. Your other half equation will be MnO4 minus going to MnO2. Again, I'm just picking out the things that aren't hydrogen and oxygen. The iodine, what is it on the left, what is it on the right, the manganese, what is it on the left, what is it on the right. You write those two half equations under alkaline conditions because it's OH minus in my original equation, whack them both together and it will be balanced and you'll be able to see your ratio. Your other option is, again, they've already written the equation for you, so to go and write all these half equations feels a bit long. You would have to use your oxidation numbers, but this is another one where the oxidation numbers are a little bit tricky. So if I'm using oxidation numbers, this is +7 and it's going here to +4, so I'm getting a change of -3. The other thing that's changing is, what's the other thing that's changing? Oh, iodine is -1 here, and then on this side it's going to be +1, so my change is +2. Isn't it? It has -2, +1 is -1. Yeah, so I'm getting a change there of +2. So what I would need to do here, again, I'm timesing that by 3 and I'm timesing that by 2. So the thing that has the +2 changes iodine, so it tells me I need to put a 3 here. And then the thing that has the -3 changes the manganese, so I'm putting a 2 there. So that's all the information it's telling me, but once I've got that done, I can fill the rest of it in. So if I know I need 3 iodines, I'm going to have a 3 there and a 3 there. The 2 manganese means I need a 2 there. I'm also going to want to have a 2 there. And then if I just balance my oxygens, I've got 8 and 1 is 9. I've got 3 and 4 is 7. So to have 9, I'm going to need a 2. And then I've got 2 hydrogens on the left, 2 hydrogens on the right. So I can see there my ratio between those two is 2:2. So it's a 1:1. And the answer is C. Actually, that one was fine. That wasn't an awkward one. I thought this one was quite awkward to balance. If you're just trying to balance it, normally there's quite a lot of trial and error involved just because oxygen pops up everywhere. It's quite hard to balance your oxygens. So what you can do here in this case, it is under alkaline conditions, but you can take this and you can essentially, if you start from scratch, it's almost easier. Fe2O3 going to FeO4 2-. So like, how would they have written this half equation? You've got 2 ions on the left. To get 2 ions on the right, you need a big 2. You've got 3 oxygens on the left. You've got 2 times 4. You've got 8 oxygens on the right. So to get more oxygens, I'm going to need to have 5 H2O, and that then gives me 10 hydrogens, and I need 10 H+. I need to balance my charges, so this side is totally neutral. This side, 2 times 2 is -4, and I've got 10 H+. So I've got a charge of +6, so I'm going to need to add 6 electrons, and then because it's under alkaline conditions, everywhere you added H+, you need to add OH-, so you've got 10 OH- on the left, and you've also got 10 OH- on the right. So those OH-, they're going to cancel out. You're going to end up with 10 H2Os, and then you need to cancel your H2Os. So those 5 H2Os will go, and you're left with 5 H2Os on that side. And now I'm back to the equation that they gave me, but it's balanced, and I can see in front of the OH minus, I'm going to need a 10. And I can see in front of the FeO4, I'm going to need a 2, and in front of the H2O, I need a 5, and in front of the electrons, I need a 6. I mean, you could do lots of trial and error, but I think it's almost easier to construct the equation yourself, and you'll see how it is supposed to be balanced. What was it? One other awkward one? Oh yeah, there's one other one in the next set of exam questions down here in the electrochem questions. Sorry, then I'll stop talking. I feel this is getting a bit long. Number 8. This one here, balance the equation for this disproportionation reaction. Again, they've given you the equation, so the obvious thing to try and do is just balance it using oxidation numbers, but it's just awkward because you've got the manganese appearing twice. So we can do it, but I think, again, what's easier is just to write this as half equations. So you've got your MnO4 2 minus becoming MnO4 minus. And then you've got your, it's disproportionation, so you've got your MnO4 2 minus becoming MnO2. So there are your two equations. If you write them both as half equations under acidic conditions, because it says it's an acid, put them together, you're going to get this, and it's going to be balanced already. And then you'll know the electrons are balanced. Your other option is to use oxidation numbers. This is +7. This is 4 times -8. That's -8, so this needs to be +7. What am I doing? No, it can't be. Oh no, this one's wrong. Sorry. I just automatically said it's +7. This one's +7. This one is a -8. This one's +6. So I'm getting a change there of +1. And then here I have a change, that's -4. So this is +4. And then I'm getting a change +6 to +4 of -2. I'm just going to write this one down here. So I'm getting a change of -2. So again, what you'd be tempted to do here is just times this by 2 and put a 2 there. But again, the disproportionation ones just are a little bit more awkward. So I've got an increase here of +6 to +7. An increase in oxidation number is oxidation. So I'm losing. You're getting the loss of 1 electron. But the +6 to the +4, you can see you're getting a gain of 2 electrons. So with my manganese, I've got oxidation and reduction occurring. I need something to lose an electron, but something else is going to gain 2. So I need 2 manganese to be oxidized so that 2 electrons are lost in total, so that my other manganese can then pick up those 2 electrons. So in total, I am going to need 3 of my manganese, all right? Then 2 of them can be oxidized, providing 2 electrons in total. The third one can be reduced, and it can gain those 2 electrons. So I need 3 on the left-hand side. And if I look here on the right-hand side, I'm going to need to put a 2 in front of one of these so that I've got 3 on the right. And the one I need to put 2 in front of is the one that's being oxidized. I need 2 of them to be oxidized, and that means I need 1 of those there. So now my manganese are balanced, and once they're balanced, you can go and balance the rest of it and quite quickly. But that was the key there, was in disproportionation, just spotting exactly how many electrons are lost, and then how many are gained. Oh Christ, that's so long. Sorry, this got really long. But hopefully it's helpful.